Hi, the 5.5, the zero-inflated count models, an example. So first we need a library PSCL. So this includes this data set and also the hurdle function and the function for the mixture model, that is the ZeroInflated function. Okay, so first this data, the biochemist's data. So this is the data set for the number of articles published during PhD. So the sample unit is students, and we have 915 students, and we have 6 variables. And the response variable is this, the ART, the articles. So this is the number of articles published by each PhD student. And several the variables, the one is the gender, FEM, and the other is the marital status, married or single, and the number of kids, the less than 5 years old, that is kid 5, and the PhD. So this is the kind of the reputation of the PhD program, and the mentor. So this is the I think that papers published by the mentor. So these are the predictors. These the 5 predictors. Okay. Then at first we try the Poisson regression model. So at first we will see whether or not it's sufficient to, this model is sufficient to explain the number of articles published. So yeah, we fit the articles on all other variables that is expressed by just dot and the data set here. Then we fit the Poisson regression model, and the pred prob function generates all probabilities. So basically the Poisson regression, we only get the parameter, but based on parameter that we get the probabilities. And this is the probability that generated by this parameter. And for the first observation, the probability of y is equal to 0 is 14%. So this student has the 14% chance not to publish any paper during PhD program. And the 1 paper with 28%, 2 papers with 27%, and the 3 papers with 18% probability. And actually it continues. So I just truncated until 4, but we have 4, 5 up to some number whose probability is very small. And also the second student, third student, and the fourth student. And think about the probability of publishing no papers during PhD program. And if we adapt these numbers for all students, then we can calculate the expected number of students who do not publish any paper during PhD program. So that number is here, the summation of pred probability, PR, and the first column. So that is 191. So this is a kind of optimized number in the sense that the overall the Poisson distribution is fit on the data. But if we take the actual, if we calculate actual the observed the number of zeros, the 0 papers students, that is 275. So overall, we optimize the Poisson parameter, but in terms of the students with 0 papers, the more observations rather than the predicted value. So we have the large discrepancy. So that directs us to include the zero-inflated part in the model. So next page is the estimation results by the zero-inflated the Poisson model. So first, the hurdle model. So we have basically the same code, but we use the different function hurdle here, not just the previous one as the GLM function. So this is the zero-inflated model. And we have 2 components. So the first component, so this is the count model component. So this is the Poisson component. And the second component is the zero hurdle model component. So this is basically the logistic model. So at first, we estimate the probability of each student having the zero paper during the PhD study. So based on this, we can calculate the probability of the first students is published zero paper during their study. Then after that, we estimate the Poisson model. So basically we estimate mu1. So mu1 is equal to maybe the log of mu1 is equal to the x times the beta, and this is the first student, so x1 transposed beta. So that we have two components, and we have these parameters and the standard error, z-value, p-value, and so on. For example, the number of papers, if the student published one or more papers, the most significant factor is this female. Actually, the female publish less paper in this data set. And also the mentor. Mentor is important to publish the more papers. And some other factors, maybe kid. The less kids, then we have more papers. And the other things, the marital status or the rank of PhD program, that does not really matter. And for how about the hurdle part? Actually this is the y1 is equal to 1. So to estimate this probability, then what variable is more useful? Actually, the number of kids less than 5 years old and the mentor. So these are still the important factor. And the women, this isn't really the important to determine whether or not they publish papers. And the marital status is the slightly significant, maybe marginally significant, unlike this count. And the PhD program, this doesn't matter really. So the rank of PhD program does not matter. So the model have two components. One is the count model part, and the other is the zero hurdle model part. And these are estimated probability. So you can see the indication of inflated number at the probability. So this 0 means the probability of y is equal to 0. And this is probability of y is equal to 1, and so on. And you can see that we have the local peak here, but also the probability of y is equal to 0 has a peak. So, and also in the second line, actually the peak is just here, but after p is equal to 0, the probability dramatically drops. So you can see that these numbers are inflated numbers. And if we take summation of these columns, this column, then we get the 275, exactly the same as the actual observations of the observed number of zeros. So next, we fit the mixture model. So mixture model, they still have two components. So one is the count part. So this is the Poisson part. And the other is the zero inflation model part. So this is basically the logistic regression. And here, actually, we estimate the phi. So that is a kind of the probability, not really the probability of y is equal to 0, but we estimate the probability of y is always equal to 0. So maybe just I put it as phi. And these parameters, at first, these parameters are very similar to the previous result. So count part. So 0.6 for negative 0.209. So these are very similar to this part. But this part is different. For example, the women have the negative coefficient and the married has positive coefficient here, but we have the totally different values because we estimate the different thing. So at first, the phi is actually a kind of probability of y is equal to 0. Actually, it's smaller than this because this is the phi plus 1 minus phi times f of 0. So it's slightly different, but the phi is rather similar to the probability of y is equal to 0. So the previous model, hurdle model, that is probability of y is equal to 1. So basically all coefficients are in the opposite direction. So positive becomes negative, negative becomes positive. And also the phi is not the entire probability of y is equal to 0. So coefficients are also different. But essentially these are the same models. So the, for example, the fitted probabilities are similar. Actually, the fitted probabilities are here. And you can see that these numbers are pretty similar. 0.216, 0.1922, and 179. So these numbers are pretty similar to these numbers, slightly different. And here we take the summation of the probability of equal to 0 again. And this is equal to the 273. So this is almost the same as the actual number, but slightly different. Why? Because this time we estimate just phi. And the probability of the y is equal to 0 is phi plus 1 minus phi times f of 0. And the f of 0 is estimated number, but this isn't just optimized to estimate f of 0, but also they have to consider the distribution of y. So it's almost, so this is almost the expected the number of y is equal to 0. The probability of y is equal to 0. But since this one is not only for the optimizing y is equal to 0, but have to optimize for larger y's, so it's slightly different. So slight discrepancy appears here. Yeah. So now you may wonder why do we have the same predictors for the count part and the zero part, inflated part. And actually, we can differentiate it. And if we write the zero inflow function, so this is for the mixture model, we can, and also the hurdle model, that we can specify the predictors for the count part and the zero inflated part differently. So in this case, the count part, we have the three variables, the FEM, KID5, and the mentor. And the zero inflated part have only one predictor, mentor. Then we can only see these predictors. So you can control the number of predictors. Certainly the zero inflate, yeah, so certainly smaller number of the variables are better. So this makes sense. And here we have 6 parameters, only 6 parameters. And previously that we have the 12 parameters because each model have the 5 parameters, 5 predictors plus intercept, so 12. And the log likelihood is negative 1605 and the negative 16608. So larger model is still better, but the difference is only 3. So 1 degrees of freedom usually that corresponds to the 2. So 2 in the log likelihood. So if we have the 6 smaller degrees of freedom, then expected the likelihood is the 12 smaller, but actually only 3. So probably this model is better than the larger model before. And we can actually test this by using the chi-square test. So recall that if the LS and LL are the log likelihoods of the smaller and larger models, then the LS minus LL, the times -2 follows the chi-square distribution with the degrees of freedom equal to difference in the number of parameters. So here, the difference in number of parameters is 12 minus 6, so 6. And the -2 times the difference of log likelihood is here, so that is 6.17. So if we test this, actually the p-value is 0.40. So that means the model, the large model, is not significantly better. So we do not reject the smaller model as a null hypothesis. Yeah, we can do also forecasting. For forecasting, basically in our function, that we have to define the new data, and the new data should have exactly the same format as the original data set to fit the data. So the original data set have the several variables, and yeah, some variables have not been used, so you can skip those. But we need these variables, the FEM, gender, and the marital status, and the kids 5, and the mentor. So at least we need these variables. So these predictors they used. Then you can predict function as this. So yeah, so we put the new data, and okay, so this is just for the new data. So this is one new observation. So so this entire line. So this is one new observations. So in general, we can have the more than one observations because this is data frame, but the one observation. So predict, so we can just predict the one observation. So we estimate the probability distribution of this new observation. And here, this is the probability of y is equal to 0, and the probability of y is equal to 1, and so on. So you can get these probabilities. So if the student is male and the single and the no kids and the mentor have maybe 6 papers, then the student have the 28% probability not to publish any paper in PhD study, but the 90% one paper, 21 maybe 22% the 2 papers, and 16% the 3 papers, and 9% 4 papers, 4% 5 papers, and so on. You can actually see up to maybe 15, maybe 19 for this example. And this is so this is the model for the mixture model. So this is phi. So for this example, it's not really, it doesn't really make sense, but we have the 2 types of student, and one type of students never publish papers. Then the probability that this student is categorized in that group is 19%. And again, the interpretation of coefficients. Poisson regression have the log link, so the mu is equal to x beta. So if we think about expectation of mu I, so that is, the mu I is expectation of x beta. So okay, so suppose x is, for example, the categorical variable is a 0 or 1, then e to the power beta makes the more meaning rather than just x beta itself. So beta itself. So expectation, the exponential of the beta has a clearer explanation. For example, the exponential of this coefficient of women is equal to 0.79. So that means that women produce 0.79 times as many papers as the baseline that is male here. Yeah, so it's easier to interpret if we calculate the exponential of the coefficient. And also for numeric variable, for example, the count of the kids less than 5 years old, then 0.88. So that means the person with the one more kid less than 5 years old, they produce the 0.88 times as many papers as the baseline. So that means the 12% less papers than the other people. I mean, people with one less child. Yeah. So these are the examples of the zero-inflated Poisson models.